welcome everyone. Today we have Nando Fioretto from the University of Virginia, who's going to be telling us about the data minimization principle, which should be very interesting.
Thank you, Thomas. Thanks for the invitation. I'm really excited to talk about this topic here. This is, as I was mentioning earlier, this is something relatively new for me. I put together those slides. It's the first time I'm presenting them. So it's this talk really, it's not meant to present some techniques that are really definitive or set in stone, but it's more a call for dialogue. It's more a call for collaboration and action. So I'm really looking forward to get feedbacks. So in this talk, what we're going to do is try to make legal principles that define the underlying principle of data minimization actionable and hopefully deployable for ML tasks. And it's going to be pretty non-technical. But let's start with some motivation. I mean, the reason why we are talking about data minimization here, it's due to the presence of AI-driven decision-making, which is instrumental for many tasks that have influential decisions in our lives. So we all heard about those tasks all over and over in the introductions of our ML papers, so I'll spare you with the details. But the point is that those ML-driven applications, they can be as effective as they are due to the presence of rich data sets that contain sensitive information. And as this amount of information grows, they also introduce privacy risk that necessitates robust data protection. And so among the risks that we are interested about in this talk are related to the disclosure of sensitive information or the acquisition of sensitive information from an unauthorized party. And so to protect against those kind of risks, several data protection frameworks have adopted the principle of data minimization. Here on the right, there's the GDPR Article 5, which is outlined. And essentially, this principle is adopted as cornerstone for addressing some of those risks. And in essence, the data minimization principles requires organization to collect, process, and retain only personal data that is adequate, relevant, and limited to what is necessary for specified objectives. So what does this mean? We're going to try to unpack those terms and in the sequence slides and try to understand what this legal language means. But the important point is that this principle is grounded in some expectation that all the collected data is non-essential for some intended objective, for some intended task. And instead, as we are acquiring more information, this information increases the risk of some privacy leakage. And so the question that we have is, how do we formalize this principle in ML tasks? And let me start with an example. So let's say that you want to buy a drink. So you'll need to showcase your ID. And then, so this ID now contains a lot of personal identifiable information, but really what you would need here, it's only a Boolean value indicating the legal drinking age, right? And so data minimization makes a lot of sense in those cases where we have some very specific outputs in a deterministic case, and where we can really connect the sensitivity of the inputs with the outputs really nicely. But in machine learning, this is not the case. In fact, machine learning context introduce a lot of challenges for formalizing this kind of principle. Firstly, what is even the objective here? Are we caring about maybe reaching some specific empirical risk value? Are we caring about bounding this risk value with respect to what we could have attained if we were using the full data set? This is not really specified. Also, when do we care about data minimization? At training time, at inference time? There is also some ambiguity in the term of the objective itself. So machine learning tends to maximize performance. We want to train a machine learning model to maximize some notion of performance, which can conflict with the principle of data minimization, because typically the more data we're giving to a model, it better performs. And thus, this makes it challenging to define what really constitutes necessary data. And so despite the legal significance and endorsement by various global data protection regulation, this data minimization principle still lacks some proper formalization for machine learning tasks. And so this is the key question of today's talk. We really want to try to understand how should we talk about data minimization for machine learning tasks. And we're going to try to do that in two settings. So training time, here we're given, I'm not sure if you see my mouse, not of course. We're given a data set, and then we want to remove some entries from this data set so that we can train a model with this minimized data set. In the second setting, instead, we are given an already trained model, and we're processing the inputs one at a time online, and we want to select the subset of features in order to achieve an intended task. So before we start, let's inspect the legal language, some of the legal language which is associated with the data minimization. So we looked at 6 distinct data protection regulation, which cover different parts of the world. So here we have the GDPR from Europe, the California Privacy Rights Act in the US, the General Personal Data Protection in Brazil, but also the regulations appearing in South Africa, Australia, and South Korea. We're highlighting parts of sections in which the data minimization principle is formalized with different colors, as they mean different things. So for instance, in green, you read in the GDPR. So I'm going to focus on the GDPR because this was the first regulation that was proposed, and typically other regulation tends to adopt language that came from precursors. So here, Article 5 says that personal data should be collected for specified, explicit, and legitimate purposes, and not further processed in a manner that is incompatible with those purposes. And then that personal data shall be adequate, relevant, and limited to what is necessary in relation for that purpose. Similarly, we find this kind of notion of purpose in the California Rights Act. It says that a business should not collect additional categories of sensitive personal data or collect additional, or use personal information collected for additional purposes that are incompatible with the disclosed purpose. So we find this notions here recurrently across all those regulations, and we then are able to categorize this language into 3 main components. What we call purpose limitation. So it's essentially specifying what requirements of the data, that needs to be collected for some limited purpose. Then in blue, it's the data relevance. So we are aiming at removing some parts of the data that does not serve the intended purpose. And then also notice in red, here I wrote data privacy, but really what those regulations do, it's defining the concept of sensitive information. And I want to notice something. In all those regulations, the red bits, they pertain to different articles or different sections with respect to those sections or articles in which the data minimization is specified, right? So the sensitive information is defined in Article 4 of the GDPR, while Article 5 defines data minimization. Similarly, in the California Rights Act, those concepts are defined in different sections, and so on. This is consistent across all the legislation that we looked at. So, and this is going to be important later on. But what are the interpretation for ML tasks? And by the way, I didn't say this at the beginning, but feel free to interrupt me at any point in time, ask questions as you have them in mind. I'm happy to take questions. So purpose limitation essentially requires that the data that needs to be collected for some specific purpose, and we should not collect extra data, right, for that can be intended for other purposes. And so in machine learning, what this purpose means, the data is collected essentially for training a model. So we could see the purpose of collecting this data for learning a model that achieves a certain level of performance, right, on a particular task. Data relevance in data minimization aims at removing data that does not serve the purpose defined. And so in machine learning, we could see this objective of data minimization here as removing or minimizing the data size while retaining the model performance. And data privacy, while it is defined as basically any information that allow you to re-identify an individual, this is, like I was mentioning earlier, it's not really pertinent within the data minimization section, but those regulations prioritize data minimization to avoid collection of some unnecessary information that can compromise privacy. So there is an implicit expectation of privacy from minimization. And so what does this mean for ML? There's three practical implications that we can derive. So firstly, there is an individualized nature in data minimization. So the relevance varies among different individuals. So take the loan approval example. If you have a score, credit score of 840, probably you don't need much more information to qualify for a loan. But if I have a score of 600, I may need to expose more information. Data minimization is also data dependent. So the term collecting data here could refer to going in the field and surveying individuals to collect some attributes, but it also could refer to the fact that we're acquiring some already available data set. For instance, I can use a census data set for training a specific machine learning model for a specific task. And we're going to focus on this setting here, on this latter setting, because it's just easier for us to design actionable algorithms in this context. And then there is this implicit privacy expectation through the minimization. But there is something that it's interesting here, because merely removing or not collecting data, it's not really sufficient to safeguarding privacy. And the data minimizations overlook the fact that there exist inherent correlations among features. And those, and once again, because this principle might not have been designed with machine learning purpose in mind. But in any way, this highlights some misalignment between the privacy expectation of data minimization or at least the data minimization which is defined in the current regulations and some of their specific requirements. So let's move to how can we basically formalize this principle for ML training tasks. And here we're going to consider a very standard task. So we're going to look at empirical risk tasks. So we're given a data set of data points xi, yi. Xi's are p-dimensional feature vectors, yi are labels. And we want to learn a classifier f sub theta, where we're minimizing this standard empirical risk function here. So we just consider this boldface X. It's a matrix of n times p items. So imagine all the data set elements by all the features that you have in the data sets. And then we're going to consider the vectors of labels associated with this data set spanning the whole size. So the goal of data minimization can be thought as minimizing the size of the data sets, of the original data sets D, by removing entries from the feature vectors. So, and here I don't mean the whole sample, right? But specific features of specific samples, as this would pertain to the data relevance aspect of data minimization, while also retaining some similar performance, right, as we would have had if we were to use the original data set. And this pertains to purpose. And so with this in mind, we've formulated an optimization problem. This is a bi-level program, where essentially what we have here, it's a matrix B, right, of dimension n times p. And this is a binary matrix. It can contain value 1 if we choose to retain that particular element in the data set, or bot if we choose to conceal it. Now, we are minimizing the L1 norm as this represents the count of the retained values. And thus this aligns with the notion of data relevance. We want to retain only what is needed. And when you are taking a column of this matrix here, and you have a pointwise multiplication with their associated feature vector, then you're retaining only the features that are relevant, right, for that particular individual. And what we want to do, so we want to constrain this problem to the space of, well, to find hypothesis here, to find weights theta hats that optimize this minimized version, right, of the data set, but at the same time, they are as close as, well, they're as close as possible within a bound alpha to the optimal classifier when we're using the same data set to assess those two classifiers. And so this constraint here, those two constraints here, they define the notion of purpose limitation. Now,
hey,
yes.
Can I ask a question? So if you're going to be cutting out certain features of specific examples, and that's not going to be consistent across examples, how does that classifier work? Do you have to do
so great. Great question. So here, basically, this bot symbol that we're using may mean many things. So it might simply mean, okay, you have an NA right symbol that you're using for concealing that particular feature, right, of that particular sample that you're not retaining, or we can use data imputation techniques to complete, to fill in that particular information that we have not completed, and so on. So there's actually various flavors, and you're anticipating a great question because there's various flavors of incompleteness in the data. In a sense here, this matrix, it's binary, so it just defines this notion of having the value or not having the value, but even there might be a full spectrum of incompleteness of this value. How correct is this value versus how wrong it is, as well as what kind of informations are we eliciting in order to reconstruct this value here. So does this answer your question?
Yeah, no, that's great answer. Thank you. It's also really interesting because I can imagine like data imputation might kind of be bad from a data minimization perspective. Like I'm trying to re-guess this information I shouldn't have ever seen, right? Like it's better than collecting the true value in the first place, but like it's maybe worse than just having like an NA feature.
Right. So I mean, from an information theoretic standpoint, if you're just reconstructing that particular data point, right, with whatever it's available, then we're not really revealing any additional information with respect to what's already in the data set. But definitely there is there might be so much correlation, right, between this particular entry and many other entries that individuals, without carefully inspecting the rest of the data set, might get access to some additional information, even unwillingly.
Yeah, I guess I'm thinking of this like old example of like how Target was able to learn that a certain person was pregnant before they even knew,
right.
Like looking at their information, like, that you could imagine, in some sense, this could be seen as imputation, and like maybe you just don't want, for example, Google to like be guessing at your sexual orientation or something, even if it's imputation.
Yeah. So I think that is a good point. I mean, so anytime we have strong correlation from a subset of features and and the labels, then there is this ability of even if we're removing any of those related basically feature, if there is enough dependency with respect to the features that are retained, and this is either with respect to this particular sample or with respect to the rest of the samples in the data sets, then where we might be able to reconstruct. Actually, this is great question, because it motivated a lot of what we were trying to do in this study here. So we try to analyze a set of reconstruction attacks. So I'm going to present a few of them here, because I think you're totally right. This notion here, it's seldomly characterizes, right, the safety of not revealing that particular data point, right? Because there's inevitably a lot of synergies between many other data points that are present in the data set.
Yeah,
So,
thank you.
I think Alessandro.
Yeah, I have a quick question. I don't know if it is addressed later. Please feel free to skip it. I kind of feel that this definition of data minimization may go against plausible deniability of the user, because if you want to give more privacy to the user, you probably want to retain more data. Like, so are you considering this? Like, suppose that you have, for instance, a simple threshold function, and even that the data is completely separable, right? And there is a single feature, right? If you want to do data minimization, you just need to retain 2 users to learn exactly the threshold. But that is probably the worst possible outcome for privacy, because now you have these 2 users that are really like the threshold is their data, right? But is this like something that you're considering?
So we haven't considered this explicitly. So we just have considered this in terms of empirical attacks, essentially, that we're running over some more quote unquote real data sets. But I agree. So inevitably, if you have some individuals that constitute some basis, right, of your space, then there is and other individuals can just reconstruct it from their combinations. Then there's not much you can say about those individuals. They become the uniqueness, right, of those individuals becomes also the weakness of this particular framework here. So I agree with you in that sense. There is this dichotomy here between how unique are individuals in this framework and how really identifiable are. And I think that there is one consideration to be taken in mind. So I think we have some, this crowd here, I'm assuming we're all accustomed to a certain notion of privacy, and we tend to think of privacy as the protecting against this kind of inference that you can do when you're observing an output of a mechanism. But I think that the purpose here of data minimization was created with probably a slightly different goal in mind, that of protecting against data breaches, right? So you have these data sets, but rather than retaining it all, now you're minimizing it so that even if something happens, then you're getting a hold of a reduced version of that data set. But what you're saying, Alessandro, it's really important, because if we're talking about privacy, we need to talk about privacy in a holistic fashion. We can't really separate concepts here. I completely agree with that point. So any other question? So I'm gonna move on. Well, this basically one additional consideration here is that privacy, it's not really encoded. So you don't see any red box here. It's not really encoded in this optimization problem, but it is implicitly encoded in this L1 minimization, because the purpose, right, of data minimization is that of minimizing, and that purpose matches with their notion of privacy. Right? So there's this obviously building those algorithms. This is a bi-level optimization problem, where the lower level, it's a non-convex optimization problem. So this is intractable. So we'll have to build some approaches that allow us to solve this problem. This is really not, I guess, if I have to, define contribution here, this is really not what I want to present as the main point of this talk. But we should choose essentially an algorithm for solving those problems. So we have a few optimization algorithms that we designed. We can approximate the lower level program using some linear relaxation, so that we can transform the problem into an IFP. Or we can learn a mapping from the original target utility to the minimized data sets, and make this mapping linear, so that once again we can solve an integer linear program. Or we can use evolutionary algorithms. They are standard in bi-level optimization. And so we have created a few of those algorithms and compared them against a few baseline, which you might use for the purpose of data minimization, like feature selection. In principle, removes something, so you might think at this as a data minimization algorithm. If we're now removing, right, the rows, it becomes some sampling. So we have a random subsampling algorithm that removes a random some individuals. And then we have an individual random subsampling. So we're combining rows and columns and remove them at random. And so let's look a little bit at some empirical analysis that we have here. So we look at three type of data sets. So a tabular data set, an image data set, and a textual corpus. And we're comparing, so we're showcasing here the amount of data we remove, so the percentage of data minimized. The highest is this number, the more we're removing, with the alpha constraint. Remember, this is how much we want to stay apart from the quote-unquote optimal, right, utility that you would have found if you were using the original data set. So the observations that we have, so firstly, you notice that for all the algorithms, obviously, as the constraints get more strict, so from 5 to 2 to 0, then you can remove less data, right? And this should be obvious. This might not arise that linearly for the handwritten digit data sets, because there is so much correlation in this data set that you can still retain a lot of task accuracy. But the key result here is that we can reduce in the tabular data sets that we tried, at least up to 95% of the entries by still retaining an accuracy gap of less than 5%, and up to 82% of the overall data sets with an accuracy gap of 2%. So there is a lot of redundant, right, information that we can actually remove from such type of data sets. And the other observation is that the optimization algorithms, they consistently outperform baselines, and that different algorithms, you notice, they have different performance levels on different tasks. And now this is important because it highlights a notion which we wanted to study, which is that of the multiplicity in data minimization. So there's many ways of achieving data minimization that they may all satisfying data relevance. And so that is no more data can be removed, right, without hurting the utility. But when we do that, what does that even mean with respect to privacy? And so here, what I'm illustrating is a task. This is on the back data set, so the tabular data sets, in which we have different runs of the same algorithm. They are all obtaining similar accuracy here, showcased in pink. But you notice the entries on the off diagonal of this matrix here, they denote the percentage of cells in this binary matrix that we had, which are retained, which are similar from each run. And so here, basically, the overlap that we have across multiple runs, it's extremely low, about 25%. That is the amount of overlap that we have. So there's many ways of achieving this minimization, which might be great because they all satisfy that relevance, but also those different algorithms and those different ways may carry different degrees of privacy risks, because we're removing different kind of information about those missing features. And so because of this privacy expectation of data minimization, which we mentioned a few times, and as you guys have already noticed, this dichotomy, right, between what we think privacy should be and what instead privacy minimization implies as type of privacy. We also run a few attacks in such data sets to understand really what can be said, at least empirically, about this notion of privacy. So we look at reconstruction attacks. Here the goal is that of recovering missing information from the minimized data sets using some imputation methods that takes the minimized data sets as well as some aggregated statistics. So we have some public subsample of the data sets over which we compute average for each features. And our scoring function measures basically goes from 0 to 1, where 0 means you can't reconstruct anything, up to 1, in which you can reconstruct all the features. There is a few observations that we can make. Also, firstly, On the y-axis here, we have the amount of data that is retained. So this is the converse of what I showed you earlier. So the amount of data that is retained, meaning at 100% you're retaining all data, you're not minimizing anything, and at 0% you're minimizing everything. One thing that you notice is that those reconstruction risks are actually really high, even when we are doing quite some good amount of minimization. So here we have 0.5, meaning that you can reconstruct half of the feature set, even when we're removing 60% of the elements in the data set. And that this reducing the data set size does not reduce the reconstruction risk linearly. And so this is an important consideration because, once again, the data minimization framework highlights this desiderata that the more we're removing, the more we should enforce privacy. Similarly, in a re-identification attack here, the goal is to identify individuals using some partial information. And here what we want to do is, so we give access to some auxiliary data sets, and we want to find data point in this auxiliary data set that such that the adversary can rank data points in the minimized data sets based on the likelihood of the match of the identity in this auxiliary data set. And so we can define this reconstruction re-identification risk score here, still as a number from 0, 1, where 0 we are not able to re-identify any feature of the individual, up to 1 we're able to re-identify them all. And we can make similar observations to what we had done earlier. So the re-identifications risks are much higher than what we should expect, even after extensive data minimization. And then reducing the dataset size does not reduce the re-identification risk linearly. So this is the case, for instance, here, where there is a plateau, and then the re-identification risk go down. The random subsampling, so remember where we remove individuals, rows, it actually behaves perfectly here, because if a sample is completely removed, then obviously it's not possible to re-identify that sample. So random subsampling is aligned with the goal of re-identification here. But there is this misalignment between minimization and privacy, because we, as we said earlier. And so something that we can do is just to add an extra term in the objective function of our optimization problem, so that we have some privacy consideration at hand. And so here we have a, basically we can modify our 0-1 matrix as rather than considering just this L1 minimization, now we consider a new score where we have some privacy consideration that are optimized either for re-identification score or for reconstruction scores. And when we do that for a given level of sparsity, we expect that incorporating privacy decreases data breaches, but potentially reduces accuracy. And here, for instance, we notice that there is a good level of trade-off between privacy and accuracy. So, so if we focus, for example, in the 1.5 column here with the coefficients beta that controls the privacy term that we're adding onto this matrix, binary matrix. If we're focusing on this term here, we can see that the reconstruction, the re-identification risk, it's cut off by 50% while still retaining high utility, right? So the threshold for the utility drop here was 5%, like earlier. So for reconstruction, the impact is a little bit less dramatic, but we can still have much of the reduction. And so this is again to highlight the fact that we, as you guys mentioned, we might need to have extra consideration, right, to consider really the real privacy risk when we're talking about data minimization. All right, so I want to now move to talk a little bit about data minimization in the second setting and inference time. Before I go there, is there any question? All right, good. So let's.
Fernando,
Yeah.
I guess I had a question. Hi, this is Adam. Maybe you could go back a couple of slides to the reconstruction risk slide. Yeah, this one. So what are the, there are like two sets of curves on each of these. There's the one with the convex arc to it and the diagonal one. So that's the convex arc is the one with data minimization. Is that?
Oh, no, actually, all those algorithms are data minimization algorithms. We use different baselines. So the red curves are optimization algorithms that that are using a bi-level optimization that we have introduced to define this framework of data minimization. So we have defined the framework of data minimization as this bi-level program here. So what we want to do here is minimizing. So we have a binary matrix, and each entry of this matrix is associated to one entity of the data sets. And so we want to minimize this matrix here so that we can remove as many entries as possible in the data set while keeping the loss for this with this new minimized data set close to the.
Right. So, okay, this part I got. What was the difference between the curves then? Like some of the curves, there were just like two very distinct sets of curves.
So the baselines are highlighted, I think blue or red, blue, and the optimization algorithms, which are those ones instead that rely on this bi-level optimization that we introduced, are highlighted red.
I see. And so the if you go back to there here, like you've got of the lines that are like lines that are kind of look like roughly x equals y.
Right.
They're not even all blue. So what's the thing that makes what is the grouping of those lines versus the ones that have that sort of clear convex?
Yeah. So basically, this algorithm here, the algorithm that have more this convex shape here are the ones that are better performing. They keep retaining more utility. This is we noticed that there's differences in the algorithm performance based on the data sets that we've tried, and also since we're using approximation, so we cannot solve this problem exactly. There's a lot of factors that might go into such considerations. But generally, those algorithms here are those that for that particular task, they retain higher performance.
I see. And did you try plotting like performance versus reconstruction? Are those different?
Yeah, we did. So I don't think I have plots here.
Okay.
So here I only have data minimization versus performance in a sense, but they are consistent, the curves, even when we're looking at performance versus data reconstruction.
So if I understand correctly what you're saying, reconstruction is pretty much just a function of performance and not so much of the actual amount of minimization. Is that correct?
In many of the algorithms that we have tried here, where we look at this pattern there. So the reconstruction statistics that also we have used, the reconstruction metric that we have used, obviously. So this is the this is the observation that seems plausible here.
I see. And do you get a similar phenomenon with the re-identification?
Here we have a little bit more.
It looks like a different behavior,
intuitions, right? Because their identification has. So what you're trying to do, you rank individuals. So for each entry, you're ranking whether these individuals belong to any individuals in this auxiliary data set. And if what you want to do, you want to match, basically have a perfect matching between the ranking of these individuals and those that are in the auxiliary data set. And so when this blue curve here, that corresponds to random subsampling, where we're just removing a random single individuals columns.
That's the dark blue curve, the straight, the one that's
the straight one. So
like
that is a perfect goal.
X equals Y, right?
Yes. So you're removing the individual completely, so it's impossible to re-identify that individual.
I see. And so what you get is that at high
Here you get.
I see. Okay. Like I guess it would be interesting to understand these lines sort of also as a function of like how useful the result is, right? Like,
right.
It's like unclear to me with these very simple kind of like algorithms if they're doing something significantly more useful than random sampling. Like the pink line that tracks the solid blue line on the left, is it doing a lot more? It appears to have like similar re-identification risk according to this metric as just dropping random data points.
Right. So
but does it have a lot better utility?
Yeah. So the utility typically it's better, but I think so there is this differentiation here between algorithms that use this optimization framework versus the algorithms that remove things at random. But the purpose is essentially the same, and the assessment of them is using the same metrics, right? So for within the lenses of data minimization, you're trying to achieve a certain level of sparsity, and that's what we care about. And how we achieve it is it's up to the algorithmic designer. And your question is, but how do we achieve this optimally? And that is a great question. The way we have formulated this problem here, it renders the tractability of the optimization algorithms an issue. So it's unless we're considering an extremely restricted class of functions that we want to study, then it's a very difficult problem essentially. But I do agree with you, and I started this talk here by mentioning that this is by no means a discussion about techniques that are presented here as definitive and set in stone, but more as a conversation that I want to have with the community to build on your feedback and on something together. So I do definitely agree that studying simpler classes of functions and extracting that knowledge from maybe objects that we can understand and study, maybe that will allow us to have at least some better generalization of that kind of aspects to more complex settings.
All right, thanks.
Yeah, thanks for the question. So maybe, Thomas, how much time do I have?
About 14 minutes.
14 minutes. So very quickly then here. So this is this. Oh, slides are not syncing. All right, so I see a completely different slide on my end. You still see the empirical analysis utility, right? Let me try to.
Oh, now I see a different slide.
Okay, good. Okay, there is some lag. So the in this setting here, so we now switch gear. We look at ML inference. Why do we look at ML inference? So I think an interesting property here, an interesting aspect, is that conventionally each user. So firstly, we have a function here, an ML framework, which is pre-trained. We're just interested in taking a set of features from an individual and outputting some result. We would like to build algorithms that select the smallest amount of features for each individuals, so that the outputs that we're getting as hopefully as close as possible with respect to the outputs that we would have gotten if we had selected all the features, right? So the interesting aspect is that generally we need all the features for inference, and this context then goes in contrast with data minimization, and that is the reason why we thought that looking at data minimization at this time, or at least looking at this process here of minimizing these features, can be seen within the lenses of data minimization. So the other aspect that it's interesting is that processing all this set of features might not only go against the enhanced privacy risks for individuals, but in many contexts, there is also a lot of human efforts that organization needs to perform in order to verify the accuracy of the information. legal sector, in banking, and so on. So there is an interesting utility here in minimizing the data. So we define here data leakage as the number of the percentage of sensitive features that are revealed unnecessarily, meaning that their exclusion would not significantly impact the model output. And the goal is to design those algorithms that reduce the amount of features for each individual as much as possible. In order to do that, we consider this concept. We call it core feature sets. So we have a setting in which we have a set of features. This is for one individual, right? So we have a set of features that are revealed. We call it R, and those that are unrevealed, we call it U. Then the set of feature R is a core feature set if for some label, the confidence of the classifier for detecting that particular label is at least 1 minus delta, where delta is some failure probability. And so this concept here of representative label, it's important because we're making prediction with limited information. And so the algorithms that we studied, they use limited information to make predictions, and make predictions that are made using just the unrevealed features. And so the representative label is going to be used in place of the actual model prediction here. And so we make two observations. First, the core feature set is not uniform across all users. So this figure reports some results based on the cumulative frequency on the y-axis of users, cumulative counts of users against the minimum number of features that needs to be disclosed to ensure confident predictions. Here, delta is set to 0, right? So those are actually confident predictions. And you notice that even for the majority, well, for at least half of the people, 2 features are already enough to have confidence prediction. And the second observation is that model uncertainty plays a crucial role in identifying the core feature set. In fact, this notion here of delta, so as delta decreases here, the model predictions become more certain, and thus we have a pure core feature set. And so the model predictions can be fully understood just by observing the unrevealed features here. And so there is a control of delta between the model's prediction and certainty, but there is also a trade-off between privacy and prediction certainty. And so here we can see that as delta increases, we need fewer sensitive features to reveal, resulting in less data leakage, but also less certain model outputs, and vice versa. Right? And so this we connect this observation with the model entropy. So we make this the relationship between core feature set and entropy, since we're using a model with incomplete information. So a pure core feature set would result in 0 entropy in this sense, enhancing the prediction accuracy, right? And so we design an online algorithm for data minimization. I'm going to be very, very brief here. So it operates in 2 phases. For each user, we're determining the next feature to reveal. And in the second phase, we verify whether the disclosed features represent a core feature set for the user. So you're given a set of features that are revealed, XR, and you have a set of features that are unrevealed, XU. Now you want to select the next feature, J, to reveal. And so what we want to do, we basically want to define a scoring function that evaluates the amount of information that can be acquired by about the model's predictions when we are inferring that, when we're disclosing that particular feature. And so here we use entropy for this purpose because it provides, we want to have features that provides the most insight for the model prediction. Right? So you probably noticed here that it's difficult to reason about the model accuracy here. So we need a function that is monotonic here. And there are challenges, there are computational challenges here. We do have some relaxation, some approximation in this paper. I'm going to skip this in the interest of time, but please refer to the paper if you like to have more details. The second phase needs to determine whether the set of features that we have revealed, now it's a core feature set. So if we're reasoning about pure core feature set, then it's sufficient to verify that the model prediction remains constant across all possible realization, which we can do in a computationally, it's computationally feasible for linear classifier. When delta is greater than 0, this property is no longer valid, and so we offer some local approximation for that distribution. And so what I want to quickly review with you are a few results. The setting here is as follows. So we have a standard tabular data set. I think this is the bank data set. So we're comparing the online algorithm in black, dmin-rel, versus an optimal model. So the optimal model here, it's a brute force method, which finds the smallest core feature set and the representative label and assume that all features are known. And then the all features model, which basically it's just the original classifier that uses all the features, right? And we consider some set of features which are public that we can use to construct our posteriors, and then we use up to 10 features. This F score here is the scoring function that we're using with respect to negative entropy, and we're comparing it against a few baselines. This one showed in the slides. It's an importance criterion. So we're essentially ranking the model parameters by the means of a logistic regression surrogate, and then choosing them based on their importance. So the key observation is that we can minimize some set of features, and even for delta equals 0, we can achieve equal or better accuracy than the baseline that uses all the feature during inference. This is really interesting, even because at some point we can achieve better accuracy as we are removing some anti-correlated features. And so data minimization can be accomplished in a sense under a linear model without really compromising accuracy so much. And also increasing delta help minimization. So here we see that the relative drop in the data leakage. Remember, this is the amount of information that we are revealing, and this is in a logarithmic scale. And so basically delta is an important component here to identify a core feature set, so reducing its size. And also the other observation is that the scoring function that uses entropy does indeed outperform other baseline for data minimization. On nonlinear classifiers, we obviously have a much more difficult setting. So here, nonlinear classifiers implements a rel neural network with two layers. The linear classifier was a logistic regression instead. And so here, unlike for linear classifier, we cannot guarantee that with achieving pure core feature set, we cannot guarantee the same level of performance of the all feature baseline. But still, we're unable to retain only a few, only 10%. So we can disclose less than half and up to 90% fewer sensitive features while achieving similar level of accuracy with respect to the conventional classifiers. And we have the same observation as earlier. So increasing delta helps with data minimization, and then the proposed scoring functions helps in terms of data minimization. So let me a few slides of conclusion here. So firstly, just to recap, we were motivating by privacy risks on different domains which use sensitive data, and we wanted to align ML frameworks with the legal language exposing the data minimization principle. But we have also seen a gap between the legal and the practical implementations of data minimization, and operationalizing this framework here has some nuances. In the context of ML training, we formulated this with a bi-level optimization problem. It's very demanding computationally. In ML inference, we formulated an online optimization. Once again, these are demanding optimization approaches. So the operationalization and the deployments of those frameworks is really challenged by the computational demands of such type of algorithms. And we also highlighted some need for privacy-centric approaches. This is especially for the training aspect. What are the open challenges? There's a lot of open challenges. I mean, this is a really new area. There's firstly, who tell us that the by-level optimization problem that we formulated is the best way of capturing data minimization? Can we? So we started thinking in the vein of DP. How would you? Can you capture this differential concept of the influence of a particular point of individuals over the outputs? We also think that there is a need for online sampling algorithms. So far, we just looked at the case in which you present us the complete data sets, and then we remove entries from these data sets. But the real minimization should actually run online and decide what to sample next, given what you already have. And there's nuances in minimization, like we were mentioning with the discussion with Matthew earlier. So right now we just remove the entry, but there are different levels of uncertainty that you might have in this data. There's different levels of removal, right? And different type of imputations that you can use to replace these entries. So this might create different flavors and different relaxation of data minimization that could be cool to study. In inference task, how to establish bounds on the leakage compared to optimal procedure. This is an open question. What kind of performance guarantees can we provide? And also, we need to develop efficient algorithms for constructing those core feature sets. One other direction which could be exciting, what does this mean to do data minimization for generative models? Is that even possible? What is the purpose for generative? I mean, those are models that you can use for many purposes. So what do we mean? Do we need novel legal language to capture the complexity of those models? And about fairness, I didn't say this, but we noticed that when you're minimizing, obviously there are different individuals with different characteristics, so you might minimize more data for some groups than others. And this creates conditions over which privacy differences are disparate. And so I just want to say that, yeah, privacy, as we all know, it's a fundamental right. I'd like to have a call for collaboration where we can delve in new methodologies for data minimization that are both respectful of privacy and compliant with legal norms. And I think that to do that, we really need not only to offer practical and technical solution, but talk with individuals that have broader expertise in legal language, so that we can really align what we are doing, and vice versa, right? So that the legal language can really align with the goals of privacy. So thanks for your attention. Okay, my slides are completely unsynced. So thanks for your attention.